Yeah, okay. So this stuff here I'm showing you, we'll reserve this for Thursday. Okay. So let me put together a little simple model, shall we? Well,
Yeah.
I think I've showed this before, actually. It's just going to be 2 steps. I want to forget it. I don't care what it goes to. K2 times S1. I don't need a semicolon there. There you go. So if I run this, I get that kind of simulation, okay? I think I can go X min. Can I do this? No, X max. Will it let me do that? I don't know. No. Okay. I thought there were a lot more. Oh yeah, here we go. What have we got here? Oh, Y X lim and Y lim. Yeah, Y lim 0, 2. There we go. That just scales the. That's a bit too much. That just scales the. It gives me a fixed y-axis. Okay. Yeah. All right. I should get to the 1 then. There you go. So now, so that's a simple reaching steady state. Okay, S1 reaching steady state. So what I'm going to do now is add an event when time is greater than 20. That time greater than 20. I'm going to do a perturbation. Let's do a perturbation in S1. You've probably seen this before already, but let's just do it. So I'm going to perturb it by 0.4. Okay. Yeah. Okay. So you see that's stable. It goes up and then comes back down again. All right. These are not the kind of perturbations we're interested in. We're interested in perturbations that cause a permanent change. So let's say K1.
Oh, it's increased.
No, it's a bit too much.
Is it reaching the infinity?
No, it goes to another steady state. No, because the axes are, the y-axis is fixed. The scale, I fixed the scaling by doing y lim equals 0, 1. Okay. Otherwise, it auto scales all the time. So this is a perturbation you can see here, right? So, but let me move it on a little bit because it's not quite a steady state, I guess. There you go. So what I could do is, the other thing I could do is at time, let me see, how can I do this? Greater than 24, I'm going to record it. I'm going to go sref equals S1, okay? So, oh, what? Okay. I have to set it up. I'll explain what this is doing in a minute. Okay, so sref is storing the value of S1 at time equals 24. So just before I do the perturbation, I'm recording the value of S1. Okay.
Okay.
You get that?
Yeah.
Now I'm going to record the value of S1, call it S1P after the perturbation. So at time greater than, let's see, it reaches steady state at about what, 45? And I'll go S1P equals
40 something. Yeah, 40.
Okay, so let's print these out. Shall we print rsref? Oops, got to get the spelling right. And rs1p. There we go. Okay, so you can see. Can you see these numbers?
Yep.
I'll give you a little gap here. I print these 2 numbers. So that's before the perturbation. That's after the perturbation, right? Okay. If I compute, I can compute the change. So yeah, I can actually also compute the delta change, which will be R1P minus R dot ref, S ref. Oops. So that's the, oops. What didn't it like? Oh, it was a cotton dot there, that's right. Okay, so that 0.4321 is actually the delta change.
Oh, I see.
Yeah, you see the delta change? Now Now, the trouble with that delta change is if I want to investigate perturbations, I could make a perturbation like this and I could record the delta change and tell you that this system is, if I perturb K1, I get a delta change of 0.4321. Ideally, I should probably take the ratio of the delta change to the value, what the delta change in K1, which was 0.1. So, okay, so let me just let's just write down what this is. So this is, this last thing is the delta S1 divided by delta K1. That's what it is, okay? So it's the change in S1, this is the change in S1 divided by the change in K1. Change in K1 was 0.1, okay? So the actual, so this is, I could make this value smaller and smaller. Actually, let's do this, shall we? Let's go delta equals 0.1, okay? And I can go delta here then, right? Then I can go r dot delta here then.
Okay.
Right, I should get the same numbers. There you go. So I can make the delta smaller, okay? And make it smaller still. What happens if I make it really small?
Like it's almost flat.
But the delta seems to be going up. But that's probably because it's not very accurate. What I really should be doing is this. What I really should be doing is computing the steady state, the correct steady state, make the perturbation, and then compute the new steady state. At the moment, I'm sort of guessing where the steady state might be, right, by using these times. So I'm going to get rid of this, and I'm going to do it the proper way. All right, I'm going to do it the proper way. I'm going to get rid of that. So I'm going to compute the steady state, okay? And now S1 ref equals r dot S1. I don't need S1 ref here anymore because I'm going to compute it outside. Then I'm going to perturb K1, okay? I'll call it delta, and then I'll take this delta out. I don't need it there anymore. I'll put it here. Whoops. I will make it 0.1, okay? Then I'll recompute the steady state. So this is instead now doing a time course simulation, right? And then I'll compute the same thing I had before, which was S1P, okay? So we don't have R's here in front of them anymore. We don't have an R there, we don't have an R there. There, no there, no there. Now I should get the same number, which was something like what, 0.43 something? Except for the invalid syntax. Why am I doing it twice? I don't need to do it twice. Oh, so 1. There you go. There you go. Yeah, it's about the same. Let me copy this into the chat so you have it.
Yeah. I'm running it. So.
Yeah, I meant to copy it before. So this is now doing the same thing as I did before, but instead of using, a simulation or time course simulation, I'm using a steady state. And this should be a better way of doing it. In fact, I'm going to get rid of that. So I'm just going to look at the delta, okay? I really don't care about the others now. So there, it's 0.34. And just to know what this is oops. This is D, this is delta S1 divided by delta K1. Right, that's what it is, okay?
Oh, I see.
All right, that's basically what it is. I'm making a change in K1 and looking at the change in S1 at steady state. What happens if I make delta smaller?
Oh.
Well, it's hardly changed. What happens if I make it even smaller? No, it hasn't changed. What happens if I make it bigger? Actually, this is a bad example. Actually, I realized this is happening because this is a linear system. So what I'm going to do, I'm going to make it a non-linear system. Okay. Actually, I'm not going to put it there. I'm going to put it here. I'm going to make this a nonlinear system, okay? There you go. Now it's a nonlinear. I'm putting a Michaelis-Menten equation, all right, into the second one, okay? Km equals 0.5. There you go. 0.4. Let's do it 0.43. All right. So now let's run that now. Oops, negative concentrations. That is because this is the old zero order reaction at the beginning that's pushing flux in, and the second reaction can't match it because the V max, which is K2, is too big. Okay, hold on. No, that should work actually.
K2.
Hold on, why doesn't it? Oh no, it's because of this K1 here. Yeah, let's push this up a bit to 0.6. There you go. What? Hold on for a second.
If K2 big, then all of them have to go to the product, right?
Oh, that's better. Let me give you an update to this one, shall I?
Yep.
Let me put that in the chat.
Yeah.
Let's see what's going on wrong here. It's the second one. It's probably K5 is. Oh, I know what it is. Yeah, that's what it is. It's got to be this has got to be above 0.6. There you go. Okay, now this is a non-linear one now. I'm doing the same thing, except I've changed the second rate law, okay, to be non-linear. All right. All right, so the delta S1 over delta K1 is 2.4714, etc. So let's start making the delta smaller. 0.1 goes to 0.81. 0.01 goes to 0.71. In fact, let's not do it this way. Let's do it a much cleverer way. Let's start a loop, shall we? Let's start a loop. Actually, what's the best way to do this? I know. I'll create an array called delta. Let me see. How do I create this? I need a NumPy, don't I?
Yep.
All right. Well, then I got to do it here then. I just want to practice something here first as MP. NumPy, what is it? Lins. I don't want a lins space, do I? I want. Can I have a log?
Already, or
Maybe I can have a lins space, I suppose. So I want to go from 0.5 to say 0.01. What does that do? Does that do it? Oh yeah, that'll do it. Yeah, okay. So that'll be these will be my delta. Oops. Grab that again. These will be my delta numbers, okay?
Yeah.
And they're slowly getting smaller and smaller and smaller. Okay, good. So now I'm going to start a loop here then for D in delta. Do that. And then I will indent that. I need to make sure that I'm starting off, need to reset K1 back to what it was each time. Its initial value is 0.1, okay? So what's happening here then, I don't need to print here anymore. So what's happening is going through all the deltas one at a time. I'm setting K1 to 0.1, so I start with the same steady state each time, right? I get the reference S1. In fact, I could just keep the reference S1, I suppose. Well, I'll recompute it every time. I then add the delta, which is D now, okay? Then I compute the steady state, and then I do this, and this is a D down here. So let me copy this into the, into the chat. Let's run that.
So SREF doesn't have to be calculated every time, right?
No, it doesn't. I could actually calculate it once, in fact. Yeah. Yeah, this is bad programming, I guess. I could do this, you know.
Makes sense.
So I'd have to recompute it all the time. I still need to set that. I still need to set that to 0.1 because I still need the delta to be from the original K1, okay? So if I run
Oh,
that,
okay.
okay, so that's good. Tell you what we'll do. Why don't we plot this instead? Even better. So let me grab hold of.
Is that the rate like delta S divided by delta K? Not really, but
Hold on, let me get the. I'm trying to find there it is.
some kind of rate.
What's the question?
Like delta S divided by delta K is what's the name for it? It's like some kind of
Well, we'll see now what it is. Let's plot the graph and then we'll know. So the x-axis is going to be delta, I guess. So x append d, and then this. Call this ratio, okay? Ratio equals that. And I shall I'll append ratio to the y-axis, okay? There we go. And then when we come out of it, I shall plot x versus y. Okay. Okay, let's push it up a bit more, shall we?
No.
We're not going to bother printing things out, I suppose. It takes forever otherwise. Although now I don't know what's happening now, do I? Maybe that wasn't a good idea. Maybe there's too many. Let's try that. So okay, that didn't work out. What am I trying to do here? Yeah, it is working. I wanted to go. I guess I can't get it lower because I really need a log distribution of delta, actually. How do I do a log? Let me see, go over here. Log linspace Python. How do I do that? Oh, log space. Okay. So if I go MP log space, and then it's start 0.05, 1e minus 6, 10. Oops. No, that's not it at all.
Oh, it's maybe because of the base of the log. Not sure.
Okay, let's see. What was the? Okay. Okay, let's just let's not put that in at all. Yeah, what do I
Just
do?
negative confusion.
Stop. I'm just looking at the help here. The base is base 10 currently. See, let's go to another help.
Space. Yeah,
it may not. It may only do increases. Maybe it's because I need to start off at a low number and then go up to say 10. It still starts at 1.
I see.
And then it goes up to 10 to the 10. Not quite what I wanted. Produce evenly spaced values on a logarithmic scale, stack overflow.
I think you can do maybe like get the lin space and then log the whole array. Like np.log and put the lin space inside that.
So you take that array and log it.
Yeah, np.log. Yeah.
Yeah, that might work.
Yeah, you might need to change the range.
Not really.
It's because it's Oh, never mind.
Because it's less than 1, right? Well, yeah.
Maybe I just need to push it down further and don't have so many points. Let's try this.
But
Hmm.
Mm.
Yeah, actually, it can only get to 0, of course. It can only go to 0 because that's the smallest delta is 0. Actually, that's as far as it goes. So yeah. Okay, so the point is, yeah, that's as far as it goes, and you notice it reaches a limiting value. That was what my point was. It reaches a limiting value. In fact, if I go, let me see. So it drops. The ratio drops, but it approaches the limiting value. Because that limiting value is the derivative. Okay. The value is about 0.70702 something. And that limiting value is ds1 by dk1. Okay, it's that. All right. So whenever you do a perturbation, I mean, it depends on your application, but in your case, I would say if you're going to do perturbations, you can't do an arbitrary delta change because the system, the sensitivity is a function of the delta change, right? You see this curve here, right? So depending on what delta change you use, you get a different ratio. The only time the ratio is unique is when the delta K1 is infinitesimally small, right? And then it's a unique ratio. And so when you do perturbations, you really want to make small changes in K1. So you're down here near the derivative. All right.
Yeah.
Do you understand that?
Yeah.
right, like yeah, like when you have the delta on the denominator, right? Like closest to 0. So
Yeah, as basically we're doing a limit, as delta K1 approaches 0. Now I can actually compute this number directly, actually. Here, let me see what value it gives me. But it's actually the UCC. I'll explain that in a minute. Oops.
So what is the
Look at that. Look at that. That's the derivative that tellurium approximates. That's the derivative we computed manually. They're basically both the same.
Okay.
So what are you going to say?
Forgot. Yeah, what's that derivative called? Like any special?
Well, we call it the unscaled control coefficient.
Unscale.
Yeah, it's d some variable, d some input or parameter. Right, so it's always d variable, state variable, or some other measurable that you're making, with respect d input or parameter, depending on who you speak to. But it's got to be the denominator has to be a non-state variable. It has to be something that's fixed. So it could be a K1, it could be a K2, it could be a Km, or it could be the X0 is also a possibility. Okay, so there's a whole bunch of possible ones. Look, yeah. So
Wait, I just got a kind of weird plot. If I run it, it's like flat.
what's flat?
Yeah, let me share it.
Oh, okay then.
Yeah, I plot like yours, but it just got something flat.
Okay.
Where's the zoom?
Oh.
Wait. That these points go up.
That's what. Yeah, you got a problem. Let's have a look at your code.
No, well, it's run fine, but then like maybe I don't know. No, it's run fine, but then I keep decreasing this one.
Unless, why is MATLAB doing MATLAB lines dot line 2D all the time?
Oh,
There's something
wait.
not right. There's something wrong with your plotting then as well. What are you doing? So you got X and Y. Oh,
Would
what's,
you-
oh, you're appending Y to X.
Oh, yeah.
What?
The X append Y. Can you see that? Yeah, that one.
Oh yeah, yeah.
It
That
should
should
be
be
instead.
D, yeah.
Okay. So, yeah, I think it should be. Wait, but it's increasing from.
You've still got a problem, yeah.
Oh.
You still got a problem up there somewhere. Let's see. Scroll up.
And X, and then I reset it, and then delta, reset it.
Append.
See the problem.
And then ratio. Oh, wait, is it this one? SB.
That's okay.
Oh,
Uh,
can you?
Oh, hold
not-
on.
Yeah,
You're not,
that line.
your
Ratio.
S1 ref is wrong. You should
So I
compute
have-
the steady state first.
Oh, I see. So put back in here.
You can either put it inside or compute the steady state outside, like I did.
Mm.
Okay.
Yeah, you can do it there.
But you put it outside,
Yeah, because I only need to compute it once.
Mm.
like where? Oh, okay.
There you go. Outside, just outside the loop.
Which one? Like I gonna bring the S rep.
Yeah,
Outside?
take those two lines, the two lines, yeah, and then one above.
Oh,
No, not that one. The one above. Yeah, that one and the one above, yeah. Cut that.
oh,
Because it doesn't change, right?
right.
So you only need to compute it
Oh, I
once.
see. I see.
Yeah.
Okay.
So it might make it a bit faster.
I see. Okay.
So people use these derivatives for all sorts of things because it's useful to know, how does the pathway respond to changes in inputs. It's the kind of thing you want to know if you're doing drug targeting or metabolic engineering. All right. Now let me go back to my one then. So I was showing you that tellurium and most of the well-known simulators have these all built in. Okay. They'll have a function to compute these derivatives for you. So this is the one that we have, get UCC. Now it's called get UCC. CC stands for control coefficient and U stands for unscaled. There's actually a scaled version too, and the scaled version is ds1 dk1, right? It's the derivative, but now we scale it to get rid of the units because this has units, of course. So we multiply by k1 and divide by s1. And that gets rid of the units. All right.
Mm.
And I get that from doing UCC. Sorry, CC. So that's the scaled one. The scaled one also has a nice interpretation. So ds1 dk1 times k1 divided by s1. That's equivalent to ds1 s1 divided by dk. I'm just rearranging it, that's all. So I've just rearranged it. I've done something naughty and split the differentials, but we're among polite company, so that there, if d were a delta, that's actually a relative change, basically a percentage change. So it's percentage change in S1 divided by a percentage change in K1. So that's why the scaled ones are much more useful experimentally, because it's much easier to measure percentage changes than absolute changes, basically fold changes. So you have two kinds of perturbations then. that you can work with. You can have the unscaled ones, which are the raw derivatives, or the scaled ones, which are the derivatives where we multiply and divide by the quantities to get rid of the units, and those are the scaled ones. So there's two types. Okay. Now, the other thing that we generally do is we compute, when it comes to an enzyme pathway, we generally compute these sensitivities or control coefficients with respect to the Vmaxes, or some linear multiplier into the expression. We don't normally look at the sensitivity of the Km, so we'd look at K1 and K2, right? So we'd look at, so I could print here, print get CC S1 K1, that would be 1, okay, and then the other one would be K2. That's what would normally be computed. Just don't need all this stuff.
Oh.
Hold on, getting there. Oh, there they are there, right? You notice actually they're very close in value. That's not an accident. I'll come back to that again later, I think. Anyway, so these are the sensitivities. So what this means to a biologist, this just means if I were to raise K1 by 1%, I would get a 1.14% increase in S1. Okay. If I were to raise K2 by 1%, I would get a minus 1.1428% decrease or decrease in S1. All right.
Yeah.
So those are the two. Those are the two sensitivities, scaled and unscaled. Now I can also talk about sensitivity with respect to the fluxes too. So I can name the reactions, and I can actually compute. I can actually compute get CC J1 K1, and I'll get the sensitivity of the flux, steady state flux, through the pathway with respect to K1. All right. Now, just to show you, Coparsi does these as well. Run that just to show you. In fact, let's grab this. Let's get this model, shall we? Call it CC. So I'll save the XML, okay? Now I'll go to Coparsi. Where did it go? I lost it. Oh, there it is. And then I'll open import. It was, what was it called? CC. There you go. There it is. So I load that in. That just contains unsaved changes. No, discard. Yeah. Okay, so I got it here now. And if I go to Coparsi, it has steady state, right? Which I can. How do I run it? Oh, here, run. So that's the steady state levels. That should be the same. I should be getting the same S1. Just to confirm, it's 0.061. 0.0614. Okay, it's the same number. All right. And then if I look at the, to get the sensitivities, I have to go to metabolic control analysis, and then I go to run, and these are the scaled ones. Okay, so it has scaled and unscaled. Okay, and they're the scaled one, 0.14286, and we had 0.14287. So they're pretty much the same. All right.
But so how do we know with respect to like
so that's the
one?
in Coparsi, the row is the variable, the numerator, and the column is the input or parameter you're changing. So they're basically changing K2 here, changing K1 there. Okay. I can also do the these are the flux ones as well. Yeah, that's the flux one. Yeah, basically 1 and 0. All right. So most of the good tools will give you these numbers.
Why is not dependent on S2?
Because there's no S2.
Oh, oh, so it's only destroy.
I've
So,
only got a simple pathway here. It's just got S1.
so if you have S2, would it be dependent on K1 and K2?
Yeah, and I'd have a K3 then probably because I'd have a third reaction.
Hmm.
So the number of species sensitivities will be the number of species times the number of reactions, actually. So that's if you have 3 reactions, you'll have 6 of them.
Hmm.
Now there's a quick way. In fact, let's do a new one, right? Let's do a new model. I wish I had some of these standard. Don't I have some I have some standard ones here, don't I? Let me see. Tellurium samples. Two-step. Okay, maybe it's samples. I really should have a 3-step somewhere, shouldn't I? Already built. Oh, 3-step. Here we go. Oh yeah. Okay. Let's do this one. Okay. Let me get rid of that. So there now is I have a 3-step pathway. Okay, 3-step pathway. Now there's a quick way of getting all the sensitivities at once, and that is by going get what is it? R dot get scaled concentration control coefficient matrix. So this is the matrix. This is all of them now. So remember I said there would be 6 here because you got 3 steps and 2 species. So it's 2 times 3 is 6. So I have 3 here. Maybe I should label these properly. Let's label
Can you
these properly.
space that to the chat?
What's that?
Can you space that to the chat?
Oh yeah. In fact, let me add this to it. Okay. So this is a quick way of getting all the sensitivities. Okay, and that's basically what coparsi is showing here. So when you look to coparsi, where is it again? Here. It's basically, this is a matrix it displays here. And it's the same matrix as this one, all right? In fact, if I go back to, if I save it, right? And then reload the model, import, CC, there it goes. And then go to metabolic control analysis, run. Okay, so if we shorten this a bit, if you compare it, you should see the same numbers. 512, 512, minus 38, minus 38, minus 128, minus 128, minus 499, 34, minus 848. Exactly the same numbers, okay? So this is a now matrix of all the sensitivities. Okay, so so it's very easy. It's just one click to get them all. All right, one command to get them all at once.
This gets scaled.
Yeah, these are the scaled. There's also unscaled as well. Just to show you what they look like. Guess it's not a little S, is it? There you go. Those are the unscaled ones. Okay. But they're generally difficult to measure because often you don't have the actual units. You know, you don't actually have the actual concentrations or whatever. You just have changes fold changes in something. So you don't only use the scaled ones. Just use this unscaled one. Just use the scaled ones. Okay.
Can it also produce the matrix of K's and S?
K's and that is the K's and S.
Oh, I see.
Yeah. So that's K1,
Oh, we have the different model. So the number
K2.
different.
Yeah, this
Okay.
different model. K1, K2, K3.
Never mind.
All right.
I see.
I can also get the flux ones as well. As the rates.
That's right. Okay.
Yeah.
Okay.
Now it's interesting here. You see all the rows are identical. That's because each of these fluxes, J1, J2, J3, they're all the same in a straight chain. All the fluxes are the same. That's what I say. So they all respond the same way. So that's why all the rows are identical.
Wait, so this one mean the chains of flux chase one with respect to the other tree?
Yeah. So this one, what this means, this is, so the rows, right, are the thing we're observing, and the columns are the things we're perturbing. So I'm perturbing this J1, which is the same as perturbing K1, and I'm looking at how the steady state in J1 is changing, and I get 0.517. So that means if I make a 1% increase in K1, I get a 0.517% increase in the flux through J1. Okay. Now, because we're at steady state, J2 sees exactly the same change. J3 sees exactly the same change. So all the column numbers are all the same. Now, if you have a branch pathway where the different parts of the branch carry different fluxes, then you get different numbers. But because it's one long chain, 3 long, each step carries the same steady state flux. A perturbation has only one basic effect then on the one flow. It doesn't matter whether you measure J1, J2, or J3, they're all perturbed by the same amount. Does that make sense? I don't know if that makes sense or not.
Yeah, but you say if you change K1, then why the flux by the flux, that you mean the rates of the reaction one?
Yes. The rate through reaction 1, rate through reaction 1, rate through reaction 2, rate through reaction 3.
Okay.
Yeah, because they're all connected, they all experience the same effect. So it's all the same. All right. Now there's an interesting observation here, and that is if you add up the rows, right?
That becomes 0.
That becomes 0, and add up these rows, they add up to 1. And this is actually a general property. It's a system. It's a property that comes out of networks. These are called the summation theorems. So. So if you're doing some training on a neural net, you'd give it these matrices probably if you want to try and train it against perturbations.
I see.
You give them these matrices.
Wait, one thing got confused, like on the control coefficient, like you say that is the delta J with respect to delta S, right?
No, it's always with respect to some parameter or input. It's never variable with respect to variable.
Oh, I see. Oh, I see. So
the variable with respect to a variable will be a correlation.
Right.
But they would only change if somewhere you had changed a parameter. Though you always have to change a parameter.
Right.
You have to get to the next steady state.
So that is delta S with respect to K1.
Yes.
Okay.
Well, actually, it's more subtle than that. It's always with respect to the linear multiplier. So whatever the linear multiplier is, okay? In fact, what this calculation does here, this one here, it actually puts in it effectively is putting it in its own linear multiplier, sets it to 1, and uses that. It's always with respect to a linear multiplier. And in fact, that's where these summations, that's why these summations emerge, actually. It's because of that.
I see.
So let me, I'm going to switch the tablet then and just summarize, okay?
Yep.
So let's just summarize. Oops. Okay. Any second now. Come on, come on, come on, come on. There it comes. Okay. So we had a pathway. Oops. Pathway. X0 goes to S1, goes to S2, goes to X1. Okay. So these are fixed. Okay. All right. And I have a V1, V2, V3. All right. And if I were to increase, let's say I have, also let's say I have an enzyme here, enzyme E1, enzyme D2. Enzymes are always linear multipliers, so that's okay. And let's say I increased E1, okay? If I increase E1, V1 goes up, right? If V1 goes up, it makes more S2. If more, sorry, more S1. If more S1 gets made, V2 goes up. If V2 goes up, more S2 gets made. If more S2 gets made, V3 goes up. So everything goes up, okay? So if I make a delta change in E1, I can measure the steady state effect it had, say, on S1, all right? And in the limit, as delta E1 tends to 0, this turns into a derivative, okay? And this then is the unscaled control coefficient. As I said, we normally scale them. So we normally take this derivative, oops,
Oh, I see.
and multiply by E1, right? The units cancel, and multiply, divide by S1, and the units cancel in S1. And then this is the scaled control coefficient. It's normally got the symbol C. Superscript is the thing you're observing, and the subscript is the thing you're changing. Okay, so it's often CS1E2. And if you have fluxes going through here, we only have one flux really going through here. So when we talk about J, you'd also talk about CJE1 as well. All right. So if we looked at this pathway with 2 species and 3 steps, we actually end up with CS1E1, and then what is it? It's CS2. Which way around is it? I don't know. I always forget. Hold on, which way around is it? Oh yeah, the variable is the yeah, that's right. Yeah, that's it. Yeah, I have CS1E2, CS2E2, CS1E3, CS2E3. That's the matrix then, right? It works like that. So that's S1, 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 E1, E2, E3, S2, 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 E1, E2, E3. Okay, that's how it's arranged. So this is the matrix then of perturbations, right? As I said, it turns out the sum across the rows is 0. Okay. And that's actually a check you can do to check that the calculations are working okay. In fact, Kapasi has a last column, which is the summation, so you can have a quick look to see that it's all right. The flux one, because there's only one flux, really there's only one row then. You only bother with one row. Oops, 3. And this summation is to 1. They sum up the row sums to 1. Okay. Now, if you have a branched pathway, you could have additional rows corresponding to the different branches, because the branches do carry different flux, and they will respond differently. In fact, to give you an idea what I mean by that, let's say I had this pathway, okay? In fact, let's say, oops, let's say this carries a lot of flux, okay?
Yep.
The most of it goes down to here, right? And a little bit goes up there. Okay, so you have J1, J2, J3. Okay. So you can imagine this like a river. You have a big river, right? And then there's little trickle coming off it. Okay. Let's say we increase this by, oops. Let's say I increase this by 10%. Right. You'd probably see, you know, maybe something like a 10% change here as well, maybe. But what effect would you see on J2? So this is where your knowledge of rivers comes in handy. So if I did say a 10% increase in the flow through J1, let's say that was reflecting roughly a 10% change in J3, what do you think the flow through J2 would be? It's a tiny, it'd be huge. It's a tiny little river. It'd probably go up by, you know, maybe 50% or something, because it's such a tiny little creek. It would be flooded out by I mean, a 10% increase in the big river is a lot for the little tributary. So that means that the flux control coefficient of J2 with respect to E1 is much, much bigger than 1. It usually is, okay?
Wait, so do you, like, you have to increase J1 and J3 at the same time, or?
No, I'm just increasing J1 and I'm seeing what's happening. So I've increased J1 by 10%. So there's a lot more water coming in.
Right.
By conservation of mass, you know, the water has to end up somewhere. So presumably the bulk of it will come down through the big river still, but it'll have a pretty significant impact on the little creek.
I see.
Because there's so much water flowing, and that translates into a much bigger control coefficient, bigger than 1. And the other one is J2 with respect to J3, E3. Oops. Oh, with respect to E3 is actually much less than 0. No, is that right? Yeah, because it steals flow from the little creek. So actually the control coefficient becomes negative. They can steal quite a lot of it. So you get these sort of amplifying effects when you have branches. Anyway, that's just a side story. The take-home message is 2 kinds of sensitivities, these unscaled ones and the scaled ones. Actually, no, hold on. 3 types of sensitivities. Scaled derivatives, 3 types of sensitivities. Unscaled derivatives, scaled derivatives, and deltas, which don't mean much because it depends on the size of delta E1, which is why, of course, we invented calculus, because calculus eliminates the issue about the size of the delta E1.
Mm.
All right.
Yep.
So you don't really use this because it depends on the value of delta E1. These two, though, these two are unique. Right? That's the key thing about calculus, right? The slope is a limiting value.
Yep.
It's unique.
If
So,
it's linear.
nope.
Yeah.
No.
I
Well,
mean,
well,
it depends.
when the D gets so small, it looks linear at that scale.
But it's a linear function, so the value is constant at every point.
I guess
Regardless
that's
of the
why.
value, yeah.
I've never thought of it that way. That's probably the reason. Yeah.
Yeah.
It's because when the delta becomes so small, the line, right, the function looks linear.
Right.
Yeah. So
Yeah.
you know, if you have a function, like that, right, and you zoom in on that, it looks linear. Okay.
Yeah. But
So,
okay.
and I guess that's the reason why it reaches a limiting value, because it becomes linear.
Hmm.
I never thought of it that way. Interesting.
I also have one question. So when do
Yeah.
you usually like do this kind of perturbation analysis?
Well, it depends on your application.
Yeah. Okay.
So for me, the reason I got into it was because I wanted to understand how these pathways work.
Hmm.
I would get all these, graphs up from the simulators, and I had no idea what was going on. So I needed some way to figure out what was going on. And it turned out that using these sensitivities was an interesting way of getting extra information out, which told me, which helped me explain what was going on. So the branch one was a good one. It helps you explain why the little creek, why the flux in the little creek is so sensitive.
Wait,
Yeah.
yeah. So for this one, is that this one, the creek is
Yeah.
like, is that the J2 respect to E2?
Yeah, that's so. Maybe I should. So there's an E1 here, okay?
Okay.
There's an E2 here, and there's an E3 here. But I'm observing J1, J2, and J3. So I'm changing E1, E2, and E3. And in each case, I'm observing the effect on J1, J2, and J3. So whereas with a linear pathway, I only had one row, with a branched one, I'll have 3 rows corresponding to J1, J2, and J3.
Yeah.
Yeah. All right.
Yeah.
So
Yeah, but like, why the control coefficient J2 with respect to E1, but not like respect to E2 and E3?
well, I can do them. I can write them all down. I just didn't. The others are not so interesting. I mean, I can go J1, E1, but that's not so interesting.
So,
And
So-
I can also write down C, J2, E2. That's also not very interesting.
why J2 E2 is not interesting?
It's it doesn't it behave this section here actually. Was it this? Yeah, the reason is this, because the creek is so small. This section here behaves as if it's a linear pathway, because the creek has hardly any influence on the main flow. The two steps that are carrying the main flow act as if they're a linear pathway, and so we've already got a linear pathway up here. So from that respect, there's nothing special about these two.
Okay, I see.
All right. What's special about a branch system are the counter ones, right? The ones the E3 and J2 and E1 and J2, and also E2 on also E3 and J2 as well. That's the other one. J2 E3 is also that one is much less. Oh, that's that one there actually.
Yeah, you see.
That's that one there.
Wait, so that one mean like when you change E3,
yeah,
you take out more of J2.
yeah, but because it's a small creek,
Right.
because the J3 is such a fat pipe, there'll be significant changes in that. There'll be a lot of water changing in that pipe, and that amount of water has a huge effect on the small creek. All right, so that's basically the way of the intuition.
But it's negative. That it means that it's withdrawing the water.
Yeah. It's because when I increase this, right? When I increase this drops.
Okay, I see.
And so this then drops.
Right.
Okay. Now the other interesting thing that happens, actually, there's one other interesting thing, and that is, I didn't want to do that. Oh, well. So this, this behaves as a linear pathway. The other interesting that happens is because J2 is carrying such a small amount of flow, if I do increase J2, it has hardly any effect on S.
Mm-hmm.
It's as if S were fixed, in fact. In fact, this behaves as if it's a completely separate pathway, independent of the other one. And in fact, the control coefficient for J2 on E2 is roughly 1. It's its own little summation theorem
Uh-huh.
because it sort of behaves as if it's, yeah, the rest of the pathway hasn't, basically doesn't notice changes in J2 because it's carrying so little water. Right.
Yeah.
So this kind of analysis helped me when I was a graduate student. It basically helped me a lot to understand what was going on in these pathways. It was a useful language to speak in to help me explain these things. The other thing we haven't talked much about are the elasticities. It turns out you can connect the elasticities to these, and so there's another level of explanation actually. So you can explain these values in terms of the elasticities, right? Which was also hugely beneficial to me in trying to understand how all these things are working. Now, for other people, these things are useful because if you're a metabolic engineer, right, you want to target those enzymes which have the highest sensitivity because they have the most influence on the flux.
Ah, I see.
Right? There's no point going for a step that has a very small sensitivity because it's not going to have any effect.
Mm-hmm.
So you try to go for the ones that have the most effect. The second thing, if you're doing drug targeting, you should also target the sites that have the most highest sensitivity. There's no point targeting a site that has very low sensitivity because the drug won't have much of an impact.
Makes sense.
And in what happens instead is, because they don't do this, right? The drug people, not much anyway. What happens is they have to up the dose for it to have an effect.
Right.
And then you get all sorts of side effects. It'd be better if you targeted the more sensitive steps, and then you were able to use lower doses of drug with then fewer side effects. So, maybe I can show you one other thing actually. Since,
Oh wait, one more thing. Like on this one, like you say, J2 respect to E2.
Yeah.
If that plus J2 respect to E1, and it's like
that's big as well. That's big.
It should less than 1, right?
No. With respect to E1.
Yeah.
No, E1. If I increase E1, it causes an increase in S.
Yeah. No. But like if you adding those two terms, like they should be less. Like
which one?
They should be less than 1. Wait, is that right?
Or if you add them up.
Yeah.
No, they'll always sum to 1. All rows will always sum to 1.
Yeah, but you have J2 respect to E1 is way bigger than 1, so
let's say it's 1.5. Yeah.
So how?
And J2 E3 will probably be
Negative something.
let me see. I'm just gonna make this right. It'll probably be something like minus 0.25, and then the other one will also be minus 0.25. So there'll be 2 here. There'll be 3. All right. Remember, this is CJ 2E1. This is CJ2E2. I've got this wrong, haven't I?
We just say CJ2E2 roughly 1.
Oh yeah, right. Maybe it's better if I do. Hold on. If I do it this way. See, I'm just going to put 1. Okay, so that's no. I'll put the J in. J21, CJ22, CJ23. The summation is always with respect to the same flux, okay, but different steps. So this one, 3 on 2, that'll be something like, minus 2, okay? 3 and 2 on J2. Oh, yeah, that'll be about 1. That's 1. And then this one must be
3.
3. Is that right?
Wait, no, that's goes.
No, 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 no,
Four.
no. No, it's got to be 2.
Oh yeah.
So they add up to 1.
Oh wait, can you say again why the middle is 1? Like why is?
Because the middle is 1 because it's this little creek here. Oops.
Mhm.
It's not carrying much flow at all, very little. And therefore, if I were to change E2, it would have hardly any effect on S.
Yeah, but like why it wouldn't be 0.2 or 0.4?
Because it's only 1 step. And for the summation to apply on 1 step, it has to be 1. So if I had 1 step, right? If I had 1 step, in fact, if I had that, okay?
Okay,
These are fixed, okay?
X1.
I got E1. CJE1 is 1. It turns out.
Yeah.
Because I've only got 1 step here, so the summation has to add up to 1. There's only 1, so it has to be 1 in order for the summation to be 1.
Okay, I see.
So last thing then, I want to show you something quickly, or I could show it to you Thursday if you want, but it's an interesting simulation I did. Where is it? I got to find it though, haven't I? Oh, here we go. Is this it? Yeah. So, actually, it's not this one, is it? It's. Oh, I'll have to find it. Hold on, where is this it? No, that's not it. Oh, this is it. This is it. Yeah. Okay, so what I'm doing here, okay, is 2 sections. There's this section and this section. The top section is a linear pathway. The bottom section is a linear pathway with negative feedback, okay? And what I'm doing is I'm generating 100 random linear chains of length 10, right? So I'm just generating 100 random linear chains of length 10.
Mm.
So that means they have random constant values, all right?
Yep.
And then loading them into Roadrunner, doing a simulation, then I'm computing the flux control coefficients, the entire matrix, okay? Then, ignore all this stuff here. Then I'm going to plot, oh yeah, well, what this bit does, it then computes the average control coefficient at each step.
Yeah.
So this gives me 100 control coefficients for each step. Then I compute the average for each step. And I plot a bar graph of the average control coefficient at each of the 10 steps.
Right.
I do exactly the same thing now, but with negative feedback instead, right? So off we go. It won't take too long. So it's doing 100, okay?
Yep. Mm.
And we observe something interesting. You think it just might be random, okay? Oh, hold on. Why do I do that? Okay, there you go. That's the distribution, the average distribution of flux control coefficients in 100 random networks. And you see there's a pattern. The actual distribution, the average distribution is not random. So we'll come back to that on Thursday, I think. Why that is the case.
Wait, so like
yeah.
you averaged CJ1 with respect to E1?
Yeah, with all the E1s for all 100 random networks. Then I computed the average for E2 for all 100 networks, then for E3. So what this axis is, hold on. I don't know why I should have been printing out all those things. So what this is the y-axis is the value of the control coefficient. The x-axis is step 1, step 2, step 3, step 4, step 5, up to step 10.
Mm-hmm.
So step 10 has virtually no control over the flux. Step 1 has most of the control, about 70%, because it still has to add up to 1, right? The whole lot has to add up to 1.
I see.
And presumably the average adds up to 1 by the looks of it.
Okay.
I don't know if anybody's proved that actually, but it must do, I guess. But anyway, there's a pattern. Even though the networks are completely random in terms of parameter values, the pattern in the average values of the flux control coefficients shows a sort of exponential or some kind of decay from high to low. Now, when I add negative feedback, that's what this is. Last one, and then we leave you then. This one, it completely changes. Now, all the middle steps have hardly any. The last step has most of it, and the first step has some. So, completely different pattern. So, we'll talk about this on Thursday, all right? As to what's going on here.
Well,
I see.
So, these numbers, they're telling you something. There's something going on here, right? There's some pattern, or there's some dynamics that's going on here that's causing this pattern.
wait, so my question, like, when you build a random network, would it be ranked as well, or just like go
Nope.
straight?
No, they're not ranked at all.
Just so it goes straight. So the only thing this control is like the K, right? The rate
Yeah.
function.
Just the E1. I'm just changing the E1, E2, E3, E4, E5, E6, E7, up to E10. No ranking. I'm just taking the average. The average values in the first step, average values in the second step, average values in the third step, all the way down, and it does this.
I see.
Strange thing. All right, so I leave you with that puzzle, and we'll talk about it on Thursday.
Yep.
So,
Thank
by
you
the way,
very
I call this front loading.
Front loading.
Yeah, I had to give it a name, so I called it front loading. One other group noticed it as well before, but nobody had a name for it, so I just called it front loading. Anyway, there's a very, very nice explanation for it. Okay, see you Thursday.
Right.
Bye now.
Thank you very much. Yeah.
From-
Have a good day. Bye bye.